Hello everyone. So welcome back. In my last video, I had discussed Reynolds transport theorem and its derivation, and thereafter I used Reynolds transport theorem to derive the continuity equation, which is conservation of mass. And in this video, I am going to consider Reynolds transport theorem, and I will use that to derive the Bernoulli equation. We will also understand where we can apply Bernoulli's equation, what are its limitation. And so without further delay, let's continue with the derivation. Let's start with the derivation. Okay, and you can comment if you don't understand. All right, so I have been always basically confused. So there are two Bernoullis that there are many. So I am just going to track their family tree and how which one is who, like who gave what. Basically, I'm trying to understand. So Nicholas Bernoulli started basically the family tree, and they were all sort of genius in mathematician, geographer, astronomer. Some gave in music also. Okay, so two people that I'm going to track is this Jacob and this Daniel Bernoulli. So Jacob basically gave one of the equation that we study in our undergrad is non-dimensional, non-linear, not non-dimensional, non-linear first order differential equation. Okay. So what is that equation? I'm just going to write it down. I'm not going to do anything related to that further. My focus is something else. This y prime or dy by dx is basically px into y plus qx into y to the power n. So this part makes it nonlinear, and this is just first order. I think you know how to calculate order and degree, right? Order and degree. So if this is basically making it nonlinear. By the way, degree is not related to this. This is just linearity or nonlinearity. Degree again comes to the power of this derivative, which is also 1. Fine. So this is the equation given by Jacob Bernoulli. That is part of math. Okay. And Nicholas 1 and 2, their family tree ends here. And next is Daniel Bernoulli, whose equation we are going to study and derive. They are the family line of this second son of Johann Bernoulli. Okay, timeline you can understand. And actually, Daniel Bernoulli gave that equation in fluid mechanics that we always come across, and he basically wrote in one of his books that relation between this pressure, velocity, or kinetic energy, velocity head, you can say, or kinetic head, and another is potential head or elevation. He talks about a relation between them for, this is very important, for a frictionless, not frictional, frictionless fluid. Okay, so as you can imagine, almost none of the fluid is frictionless, right? So but this is huge idealistic assumption, really away from the real fluid. Okay, so other than this, Bernoulli didn't actually derive this, and whatever I'm saying, I have taken a reference from standard books, for example FM White and notes that I studied. Okay, so basically in this was somewhere in uh, okay, I forgot that. Fine. So but later on, this Leonhard Euler in 1755, he actually derived the complete equation. Okay, I recall one more thing. So this Jacob person, firstly in his book or in his notes somewhere, the integration word came for the first time and its meaning. integration. Okay, okay, fine. So integral came from his realm. So let's start with this thing. Okay, derivation of this uh, Bernoulli's equation, or you can say Euler equation later on. So Bernoulli's is very this idealistic form of fluid. Okay, so this video is going to be long, right? Fine. So how, let's start with this. So I'm going to consider a fluid flow along a streamline. Okay, so this is another one of the limitation. So let's say I'm going to consider a streamline in this direction S, and let's say its area of cross section is going to vary. Fine. So pressure force, by the way you estimate pressure force is Fp is equal to basically minus P n cap and dA. Okay, so n cap is basically outward normal vector of cross sectional area. Okay, so this is how that means pressure force is going to be normal to the surface, normal to the surface. Okay, and always inward. Fine. So this is it. Now I'm going to, I can erase this part, right? I think it must have been recorded, and yeah, it is recording, and fine. So I'll just remove maybe this part, and then pressure here is going to be P, and here pressure is going to be P plus dP, that we are going to assume, and let's say rho and velocity field, right? Velocity field, and rho plus d rho is going to be, and velocity plus dv. Okay, so here as you can see P plus dP, I have done it inward again and perpendicular to the area vector. Okay, now since this is our biggest assumption, right, frictionless fluid, that means viscous, it's non-viscous fluid, inviscid fluid. So but I'm going to, if you were to apply tau or shear stress, it is going to be like this. Okay, and but you can assume, it's always a wise idea to show, to write it down and then cancel it out, make it zero. Okay, so another thing, we have considered this streamline. So imagine this area element, right? This is, of course, in this S along the streamline, this area, this whole element can be considered as single streamline. I'll repeat myself. So this we have considered this element along the streamline, but whole element can be considered across as a single streamline. Okay, a streamline, I think you can easily understand a streamline. What is a streamline? Basically the velocity field is tangent to the actual path of fluid. So okay, and we have assumed this is theta. Okay, and this is dz. If we are considering a area element, basically dA, then along this ds, and this is we have what, this is the direction s. Okay, and d theta. Okay, now just because I'm explaining this figure, what I can do is I can have the gravity, body force, basically the weight of this fluid element, and what would that be? Rho g into elemental volume. Okay, now what else I can do that from here? Maybe we can simplify this, or maybe later. Let it come, the force thing, let it come. I'll come again and do that. Okay, so let's see. So first thing what we will do, we will apply Reynolds transport theorem, let me just write it down. Okay, you can go back to my previous video and understand. uh, B can be any parameter, and dB by dt is going to be, okay, and this is basically rho, and beta is basically nothing but B by mass and dV. Okay, so if it is B by mass, okay, plus what would be rho beta and velocity field into d area, and this is out. Sigma you can do, because multiple faces can be present, and rho beta v dA in. Okay, this is our Reynolds transport theorem. So what we are going to do here is we are going to apply this for conservation of mass. Let me use some other conservation of mass. So again, if you are using this V is equal to mass, it could be any parameter. I have explained it in my previous video: energy, power, pressure, or anything, energy, momentum. Okay, so on this left hand side, it would be mass, rate of change of mass, right? Mass is always conserved, so that part would be 0, and here d by dt. Just hold on a second. Okay, just one small change that I was afraid. So basically it's d by dt, right? It's not partial. It will become like that. I will tell you how. So b is this, right? So what I get, d by dt, and this is going to be rho, and beta would be 1, right, into d this, plus here what would be basically rho v and dA out minus rho v dA in. Okay, I can write on that side 0, or in this side, that is fine. So can I write this thing as dm, right? Not this thing, like complete dm is the change of rate of mass, right, for an element of ds size and cross sectional area dA, like that. Okay, for a small element. So another thing, in my figure here, rho and yeah, here let me choose this rho, what else is velocity, pressure, these all are function of s and time. Okay, but for a small element, for a given cross section, this can be same, right, because it is varying with s. Not with, of course with respect to time it will vary, but for a given cross section, I can take this rho out and it will become partial, right, because it also depends on s. And this dv, so basically this term d by dt rho dv, this can be approximated as dx, sorry, ds into, I have been using capital S, sort of. It's the smallest, but the way I am writing, into dA, right? And then plus this is going to be dm dot is equal to 0. So this I approximated like this, and then this. Okay, now, or basically s into dA, right? We have taken one whole element here. This. All right. All right, so basically what we have to do now is we have to approximate this d by dt and rho dv. So this can be written as approximately, since we saw rho is a function of s also, and dv is going to be a into ds. We are considering ds length of that streamline. Okay, wait, that streamline in s direction, if you remember. Okay, and then this dm element, what else we can write here? D of this is nothing but rho a b. Okay, so what we have here, dm, this d rho a b is equal to minus del rho by del t into a ds. Okay, fine. Now what we have to do is we have to apply momentum equation using RTT. Okay, in my next video I will derive the Navier-Stokes equation. Okay, so we will be using RTT multiple times, and you will actually get used to the fact how we can apply in any scenario. Okay, so RTT is there. Okay, what now? Oh, momentum equation. So in momentum equation, what you can do is beta is equal to m into b. Sorry, b is equal to m into b, and beta is going to be b. All right. So just all right. So when you apply here, so basically total force F is going to be what? It is going to be d by dt, just like the last time, rho beta and this, right? Rho beta and dv. So beta is b by mass. Basically it should come rate of change of linear momentum. Is it coming? We can check quickly. This is mass upon volume. This is mv, right? So d by dt. Fine, this is correct. And here d times rho av, or you can say, let me write d times m dot v. Okay, so how can we again, so we can approximate this like how? Tell me. So del partial rho by partial t into velocity, and this is a into ds. Okay, and plus d m dot into v. Okay, this is your sigma f, and sigma f is basically what are the forces that it will comprise? See, viscous force has been neglected. Okay, what else now comes the pressure force, and then other one being what else, body force or gravity force, weight, basically weight of that fluid element. Okay, let's work on the weight and then we'll work on the pressure force. So where we are here, we estimated this weight, right? Let me use here. So basically rho g, and it can again be approximated as a into ds, right? Now tell me one thing, which component of this force is going to act along the streamline? So this is theta, right? So cos is going to be perpendicular, and sine, it's sine component, right? So basically f g along s, how can we write? Minus rho g a ds sine theta, right? So ds sine theta would be how much? Tell me. Ds sine theta. So ds cos theta and ds sine theta is nothing but dz. Okay, sine theta is equal to dz upon ds, and you can put it here. I hope you are able to understand. Minus rho g a dg. Okay, and this rho g sometimes is written as gamma, minus gamma A dg. I don't know, like fine. It's a specific gravity, I think, or a specific weight, not a specific gravity, a specific weight we can say. So that's the way of representation. We are going to need this, so we can keep it like this. So forces we were doing, right? Gravity force, how much we got? Minus rho g A into dg. Okay, along the this streamline. Now pressure force, to understand pressure force, it is little bit tricky, and I'm just going to make another figure here to explain you the same. So this was our element, and okay, so what is going to be, see, this pressure P at cross sectional area A is going to act everywhere, right? Here also. And what would be pressure here? P plus dP. And what would be area? A plus dA. Okay, so this pressure P is added here also. It will be added here, here, here on the surface, here, here, everywhere, right? So what we have to understand is we have to find out net pressure force. Net pressure force in which direction? In S, in the line, in the direction of streamline. Net pressure force in the direction of streamline, which is S. Fine. So what we can do is we can it would be like final minus initial. So press that P can be not neglected, right? It can be subtracted. So effect of P, we can neglect it from the beginning. Okay, area will be there. So fine. So net, so we can now let me make the diagram here for something without the pressure. Okay, so basically here is going to be what pressure? dP, and this is going to change like a, this is how it is going to be inward, right? Okay, and here we have dP at cross sectional A plus dA. Okay, now tell me one thing, consider something like this. This is the streamline direction and something is acting like this. What would be and this is theta and this is again theta. One, what is the component, its component in yes, so this slanted height, do not consider it at two places, one here and one here. No, do not consider it like that. Consider a continuous roll. Okay, along the periphery curved surface, somewhat like cylinder or conical frustum. So here this P, this is also dP, right? Sorry, so here pressure is P plus 0, P plus little bit more, P plus, and finally here P plus dP. I hope you understand. That is very, like, intuitive, I would say. So what I'm trying to explain here is this. Let's take component. One component would be along this and other would be along this. And similarly, let's say on the other side or on at some other location on the curved surface, it is going to be something like this. So again, what would happen? One component like this and other would be like this. So they will cancel out each other. I hope it is clear. Okay, vertical component will cancel out, only this component will be present. Okay, so and that component also is going to be along the positive direction. And what would be that component? That, let me call it fp1. That is going to be basically average force into area of cross section. So we are only considering the change in area, right? So average force is going to be half plus 0 here and dP here, dP by 2 into d area. And what would be pressure here? Change in pressure we are considering only. You'll take a while to be able to appreciate it. Believe me, I didn't get it either when I was going through it. So dp, it's negative direction, minus dp, and here it is going to be area of cross section, that is plus dA. So we can call it fp2. Okay, so what would be net force along the streamline? Half dp into dA. I hope it is recording, right? Yeah, I have done that. Do not press the record and all the effort is wasted, right? So minus dp a plus dA. Right, now tell me one thing. So what I'm going to do here is, you must have done binomial theorem, right, where higher order terms are neglected. And higher order terms also, whenever let's say dx dy is there, or somewhere dx square is there, dx cube is there, something like that, or you consider h in binomial, right, h cube or something, so you neglect it. That neglect higher order of that change, small change, because you multiply 0.01 into 0.01, you will get 10 power minus 4, which is very 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 small. Okay, so this and this, I'm not cancelling them out to each other, rather than that I'm neglecting. Okay, let me write down neglected. Okay, so fp, it turns out to be what? Minus dp into area. This is not rho. Okay, now let's put sigma f. Sigma f is what? Minus rho g and area, what was that? Yeah, minus rho g a into dz plus this one, which is minus dp into a. And this whole pressure force was equal to what here? This term. Okay, I'm just using that, this equation, right? You can come back and just take a relax and take a look. So when you will equate both of them, what will you get? Let me write it down here. Minus rho g a dj minus dp a p. A is equal to del rho by del t, del rho by del t a ds, del a ds v, velocity is also there, plus d m dot v, right? So let me just open it down. So what will I get? Rho v, I think just one thing. See, one minor comment or mistake, I would say. This can be huge if you don't. So see, rho and v both are function of s and time, right? Location and time, so they will be out in partial derivative with respect to time and rho v. So this rho v area into ds plus, when you will again break these, what you will get? M dot dv plus v dm dot. Okay, now what can I put in? M dot rho a v. M dot is nothing but rho a v. Fine. So again, similarly, you have to break it down here the way you broke it there. So let me just change the color. So here what will you get? Del rho by del t into av ds. Now this velocity has come out of this bracket, plus rho a ds. Let me write del b by del t like this. Okay, plus rho av dv plus v d rho a v. Okay, now tell me one thing. And okay, what is on this side? Minus rho g a dz minus dpa. Now let's recall the conservation equation. Recall the conservation equation. Okay, when you will recall the conservation equation, what have you derived? What we did? Yeah, okay, here, this one. So d rho av is equal to this, d rho av. So d rho av is this, and d rho av is equal to what? Minus del rho by del t a into ds. Okay, and when you will put that, you will get this term. Okay, del rho by del t into av ds. So they are opposite sign, they will be cancelled out. Okay, and what is remaining? And let's also at this stage only divide both side by rho into a. Divide both side by rho a. Okay, what is remaining here? If you'll divide, minus g dz minus dp by rho is equal to, so this is going, rho a you have divided, right? So this is going to be partial vt into ds plus v dv, right? That's it. Now take everything on one side, and that is going to be your final equation, and it is going to be ds plus v dv plus g dz plus dp by rho is equal to 0. This is your Euler equation, and let's simplify it further to reach to the basically Bernoulli's equation. So there what you will do, you will have to first consider, okay, so tell me one thing, when you will try to find out, this is going to be, right, basically from 1 to 2 some location on the streamline, 1 to 2, 1 to 2. So we will consider two things to simplify it down further. And what are those two things? First is incompressibility. Okay, incompressibility, that means density is not changing, right? And steady state, when you will consider steady state, this term goes away. Velocity is not changing with respect to time. What else? Incompressibility, then density is going to come out, right? So what you will have, p2 minus p1 by rho plus half v2 square minus v1 square plus g z2 minus z1 is equal to 0. So this is basically the Bernoulli equation that I was talking about. Okay, so let's now consider what are the condition under which this Bernoulli's equation are applied. Okay, all right, so what actually I'm going to tell you four conditions. Let's say first is steady state. Okay, so no temporal change. Second is incompressible. Incompressible, that means density is constant for the condition that Mach number is about 3 or less than 3, not about 3. Mach number is less than 0.3. Basically, if a fluid air, if if air is flowing at about 100 meter per second, which is equivalent to any commercial our passenger planes and all, beyond that it may be this incompressible thing may not work. Okay. Okay, so this is third is flow along a streamline. Flow along a streamline. Okay, another important I left out, let it be fourth. This is, let it be fourth. Third is basically frictionless. Okay, frictionless flow. Okay, and whenever we talk about this frictionless flow, almost all of them are irrotational. Irrotational flow. Basically, rotational feature comes due to if a solid boundary is coming, or some mixing is happening in case of turbulence. So basically, in case of turbulence, so basically, uh, this thing, viscous dissipation has not been considered. This is 0. Okay, for real fluid we will consider Navier-Stokes equation, which will take a lot longer than this video, and you have to be patient for that. Okay, and along a stream, so along a streamline, what actually happens is there's something called, you can say, p1 by rho plus v1 square by 2 plus gz1 is equal to p2 by rho plus v2 square by 2 plus gz2 is equal to constant, and this constant is known as Bernoulli's constant. And what is the condition for this? This flow, all these four conditions should be satisfied. Now, another interpretation is in terms of energy. Basically, this is the summation of reversible pressure work that you study in thermodynamics, and kinetic work and potential energy. Okay, and there is no work done due to the viscous dissipation or shaft work or any other exchange of work through the in the system. Okay, so I think this was it. Thank you so much for watching the video. Do subscribe to the channel and stay tuned for derivation of Navier-Stokes equation in the next video. Okay, and you can comment your you know if you have any doubt or if you have any feedback to give me, and I would be happy to take it. Okay, thank you.